Our last topic in this module is reaction stoichiometry. Balanced reactions can be used in the same way you used formulas as conversion factors. Now, the word stoichiometry has, I don't know, maybe some scary connotations, but what it is saying is just you have a balanced reaction. It means that everything fits together in these perfect proportions and you can use it to go wherever you need to go with calculations, with figuring out how much product you're going to make, with figuring out how much of a reactant to use, and so much more. We're going to look at a reaction of 2H2 plus O2 making 2H2O. Now, I'm also going to put in the implied 1 in front of the O2 just so that we don't forget about it. This is not something that you're required to do. And the question that we're going to answer is if I react 0.982 moles of H2, how much O2 in moles do I need? And it's really asking, like, how much do I need to perfectly react with this amount of H2? From my balanced reaction and the coefficients with my implied 1 written in, I can see that for every 2 molecules of H2, I need 1 molecule of O2. To kind of phrase it the way we did when we were balancing reactions. That means for every 2 moles of H2, I need 1 mole of O2. And that's our conversion factor. So starting from 0.982 moles of H2, I can write this, right? It's the conversion factor. They're equivalent to each other. I could write it with moles of O2 on the top or moles of O2 on the bottom. I mean, we are trying to get to moles of O2, so that should be what's on the top. And moles of H2 is on the bottom, so that moles of H2 cancels. And from the coefficients, I know that 1 mole of O2 is needed for every 2 moles of H2. This is a conversion factor from the balanced reaction. Moles of H2 cancels, and I'm left with moles of O2, and because I also had to divide by 2, numerically, my answer is 0.491 moles of O2. That is the basis for all stoichiometry calculations, and you can relate any one thing in a balanced reaction to anything else in that reaction. So I could have also asked, how much water would we produce? Or I could have given you an amount of water and asked, how much H2 should we start with? And so on and so on. Now, this is when everything works perfectly. Of course, our next section is when it doesn't work perfectly. So we're going to talk about limiting reactants. When things are not perfect, when you don't put in perfect amounts of every reactant, one of the reactants will limit how much product is formed. So we call it the limiting reactant. We call the other one the excess reactant because we have an excess amount of it. As a great example, let's make s'mores. So I'm going to write the recipe for a s'more as a reaction equation. So you need 2 graham crackers, 1 marshmallow, and 1 piece of chocolate to make 1 s'more. So you need 2 moles of graham crackers plus 1 mole of marshmallows. This would be a lot of s'mores. Plus 1 mole of chocolate to make 1 mole of s'mores. Okay, this is a reaction equation. If you have 18 graham crackers, 10 pieces of chocolate, and 7 marshmallows, how many s'mores can you make? I know you can probably see the answer. I want you to pause the video, figure out how many s'mores you can make, and then come back so we can talk about the process. Okay, whether or not you paused, welcome back. So the answer is that with this amount of each thing, the most you can make is 7 s'mores. So how did you figure this out? What was your process? Your process was probably, even if you did it so quickly in your head, that you calculated the amount of product you could make with each of these reactants and then chose the smallest one. Right? With the 18 graham crackers, we could make 9 s'mores maximum. Right? So if we're going to do exactly this with chemicals, let's do it with unit conversions as well. So the 18 crackers, from my balanced reaction equation, I know that for every 1 s'more I get, I need 2 crackers. This means I could make 9 s'mores from my 18 crackers. Just from the chocolate and my balanced equation, 1 s'more requires 1 piece of chocolate. So from 10 pieces of chocolate, I could make 10 s'mores. My 7 marshmallows, 1 s'more requires 1 marshmallow. Therefore, I could make 7 s'mores from my marshmallows. The least amount of s'mores I could make is 7. Therefore, marshmallows are my limiting reactant. So the marshmallows limit the amount of product that I can make. And what this means is that if I'm going through, I have all of this stuff, I'm assembling s'mores, I make 7 s'mores, I go to make s'more number 8, and I can't do it because I don't have a marshmallow. It means the same thing in a reaction. It goes to make the next molecule of the product, and it can't because one of the reactants just ran out. That's what the limiting reactant does and what it means for something to be a limiting reactant. And now we'll do this with chemicals. The reaction that we're going to do, we will combine 400 grams of sulfur dioxide, 175 grams of oxygen, and 125 grams of water. I want to know, what is the limiting reactant? And because this is a reaction that I would not expect you to know or how to put together, I am also going to give you the balanced reaction, which is 2 SO2 gas plus O2 plus 2 H2O makes 2 H2SO4. So the process that I'm going to use is exactly what I used when I was calculating how many s'mores I could make and figuring out my limiting reactant there. I'll take 400 grams of SO2, 175 grams of oxygen, and 125 grams of water and figure out how much product I can make. So I've got a few added things in here that I need to do in order for this calculation to work. So I'm at grams of SO2. I need to use mole ratios to relate things through the equation. So I have to convert SO2 from grams into moles. So I need to calculate the molar mass and incorporate that into my calculation. So 400 grams of SO2, 1 mole of SO2 has 64.07 grams. And from my reaction, 2 moles of H2SO4 are made for every 2 moles of SO2 that I put in. This means that I could make 6.24 moles of H2SO4. That's my maximum amount that could be made from the SO2. For oxygen, convert the oxygen to moles. Don't forget that it's O2, which makes my molar mass 32 and not 16. Then from the reaction, I get 2 moles of H2SO4 for every 1 mole of O2, which means I could make 10.94 moles of H2SO4. From 125 grams of water, I can convert that to moles of water, and then for every 2 moles of H2SO4, I need 2 moles of H2O, which means I could produce 6.94 moles of H2SO4. Now, I stopped at moles for calculating the amount of product. You could go all the way to grams. It's not necessary because we can compare the amounts in moles. And from the amounts in moles, 6.24 is the smallest. That means SO2 is my limiting reactant. When it goes to make the very next molecule after making 6.24 moles of molecules, there's no more SO2 left, so it cannot make the product. The other question that you might have, this reaction only has one product. What happens when you need to calculate the limiting reactant for something that has multiple products? Don't stress, because it doesn't matter which one you pick. You can pick any product as long as you calculate the amount produced for that same product from every reactant. So pick one and stick with it. My hint, wink, wink, nudge, nudge, is to always look ahead in the problems, because sometimes one of the products you pick will be more helpful than the others. As in, you're going to need an amount in a later part of the problem, so you might as well just calculate it first. Okay, so I've identified the limiting reactant. From here, I want to add a couple things to this. So that's the limiting reactant, that's 6.24 moles of H2SO4 that can be produced. That is the theoretical yield. That means if everything is perfect, the reaction goes beautifully, nothing goes wrong, nothing is lost anywhere, it's an A+ day, like everything is literally perfect, 6.24 moles is the maximum amount of H2SO4 that I can make. Now, we usually report theoretical yields in grams, because then when we measure the amount of product we actually get later, it's probably going to be in grams. So all I have to do is convert from moles to grams with the molar mass. So the theoretical yield means what is the maximum amount you could produce from your limiting reactant. In this case, because the molar mass of sulfuric acid is 98.08, this means I could produce a maximum of 612 grams of sulfuric acid. Now that's in the beautiful perfect world scenario. Now, when you actually run the reaction, this unfortunately doesn't happen. So here is an example, right? When the reaction was run in lab, the chemist collected 517 grams of sulfuric acid. This is what they actually collected, so we just call it the actual yield. This is the real life, what I got from the reaction. Now, if I told someone that I did this reaction and I got 517 grams of sulfuric acid, they have no idea. They have no way to compare or know. Well, first, they're probably going to think I'm a weirdo and I should leave them alone. But they have no idea if that's good or not, because they don't know what I was supposed to get out of the reaction. This is why we report things as percent yields. So the percent yield is a way to communicate that 517 grams was good, bad, normal, anything else when we share that information with someone, which chemists do all the time, right? The percent yields are in the literature papers for people who synthesize chemicals. The percent yield is how much did you get compared to how much you were supposed to get. So actual yield divided by theoretical, and then multiply by 100 to report it as a percentage. So 517 grams when I was supposed to get 612, that's an 84.5% yield. This is like primo. This is an amazing yield. And it might not seem amazing, and that's because your brain does percentages as grades, and you might not be happy with an 84.5%, but let me tell you that there are chemists who would sell every belonging they have ever had to get a reaction with a 30% yield, because there are some reactions that whatever else is going on, whatever other processes you have to do, the percentage yield is not that great. Now, it means, right, Just like with grade percentages, a percentage yield in a reaction is not a sign of your moral fortitude or anything like that. It's just saying, compared to the 100% perfect day, how did I do? And in this case, 84.5%, that's pretty fantastic.